this college algebra lesson, we're going to talk about functions and their graph. Let's first start by defining what a function is. It's a correspondence between a first set, which we call a domain, and a second set, which we call a range, such that each member of the domain corresponds to only one member of the range. In our first example here, it's asking us to determine whether each of the following correspondences is a function. So I'm going to first draw lines from -6 to 36, 6 to 36, -3 to 9, 3 to 9, and 0 to 0. On the left, I'm going to call these my domain,
in our domain,
and on the right, I'm
such
going
as
to
George
call this
H.
my
W.
range.
Bush,
Since
Bill
each
Clinton,
member
and George
of our
W.
domain
Bush
corresponds
correspond
to
to more
exactly one
than
member
one
of the
Supreme
range.
Court justice.
This is a function.
This is not a function.
Now let's look at appointing a president.
Determine
and the
whether
Supreme
each
Court
of the following
justice.
correspondences
So George
is
H.
a function.
W. Bush
It's
appointed
telling us that the
Samuel
domain is the year
Alito
in which
Jr.
a presidential
and
election
Stephen
occurred.
Breyer.
The person elected
William
is
Jefferson,
the correspondence and a
Clinton
set of presidents.
chose Ruth
So we're having a list of all of our presidents here,
Kagan.
the years in
George
which an
W.
election
Bush
occurs,
chose
and then the
John
person
Roberts
elected is our
Jr.
arrow.
and Sonia Sotomayor.
We can say that
And
this
finally,
is a
Barack
function
Obama
because
chose
each
Clarence
president
Thomas.
election only
Let's
has
graph
one
the
president
following.
elected. We
Of
never
our
have more
function,
than one
f of
president.
x is
So
equal
it's
to x squared
distinct.
minus 5.
Let's
First
look
of
at the
all, I wanna
domain
know
of
what the
all
shape of this
automobiles
is.
produced in 2006.
I know it's a quadratic
The
because the highest
correspondence
power of x
is
I
a
see
vehicle's
is
VIN
a
number.
square.
And the range
And then can you
are
go
all of the
ahead
VIN
and
numbers
substitute
possible.
each of my x
This is
values
also
using
a
my
function
table of
because
values.
each automobile
When
only
I do
has
that,
one
I end
VIN
up
number,
with the
and
following
each vehicle's
points.
VIN number is unique to
I
itself.
then plot those points.
When I look
and
at the
see I
domain
end
of
up
the
with
set
a
of all
parabola
professional
where my
golfers
points
who won a
match
PGA
exactly
tournament
what I
in
discovered.
2014 and correspond them to the tournament won.
When I
The
want
set
to
of
graph
all
f of x is
PGA
equal
tournaments
to
in
x cubed minus x,
2014.
I
We
know
can
this
say
is
that this
going
is
to be
not
a
a
cubic
function
curvy
because a winning
shape
golfer
because I have
could be
x
paired with
cubed.
more than one tournament.
Let's go
because
ahead
it is
and I'm going to
possible
show
for a
you
golfer
how
to
I can
win
do
more
this
than one
using
tournament.
Desmos.
But let's reverse it. Let's say that the domain is instead the
I
set
have
of all
my split
PGA
screen
tournaments
here
in 2014.
where I have my problem
the correspondence
on the left,
is
and I
the
have
winner.
Desmos
and
on
in the
right
range
here.
are all of the golfers.
I'm going to type in, because we
Well,
know
since
f of
each
x is
tournament can
fancy
only
wording
have
for
one
y,
golfer,
I'm going
we
to
can say that
this
y
is
is
equal
a
to
function.
x cubed minus x.
A relation is
Notice
a
on Desmos
correspondence
that we
between
have some
two
key
sets
points
that
are listed
and
here.
is not a
These will
function.
be important
It
points
still
for
may
us.
be
These are
an
called
example
turning
of a
points. We're gonna
relation.
talk about these
A relation
points
is the
little bit
correspondence
later in
between
college
a
algebra.
first called a
But
domain
let's say I
and a
want to fill in
second
my
called the
table.
range.
To do that, I can
Such
click
that
my
each
settings
member of the
list,
domain corresponds
and then click
to
the table,
at least one
and it will
member of the
auto-populate
range
some of the
versus
the points for us.
function
But I don't
must
see that I
only
have negative
one
half
member
listed.
of the
I can
range.
click in
This
the
one says
box
you can have
and
more
simply
than one.
type
So
negative
let's draw
1
function divided by
arrows
2
from our points,
and I see that
from
I
the domain to the
outpops
range.
3
So
eighths,
9 goes
which in
to
decimal
negative
form
5.
is the same
9
as
also goes to
375
5, and 2
thousandths.
goes to 4.
I can also
We can
hit
say
enter
that
or
this
click
is
into the next
not
box
a
and put
function
half,
because
gives
9
me the
goes to
negative
negative
version
5
of 3
and
eighths.
as well as 5.
Also, you
So
might
a
have
member
noticed
in
that
the
when I
domain
typed
goes
these
to
values
more
in,
than one range.
there was
Our domain are
pieces
all of
here
our
that
x
popped up
values.
for us,
So all of our
or
x
points.
values are 9 and 2. And then
Now,
our range,
I know
our y
that my
values
next
are
problem
negative 5, 5,
is going
and
to be
4.
a radical
Let's
or
try another
square root
example.
function
Because
because
we
we
have
have
a
a
square
goes
root
to
listed.
5.
Let's go ahead and
5
graph
goes
this
to
one.
7.
So I'm going to click
The
0
x
goes
and
to
get
1,
rid of our
4
equation.
goes to negative 2.
Down below,
Each
there is
member
a little
in our
keyboard.
domain
If we pop that up,
corresponds
we
to
can
exactly
find the
one
square root
member
next
in
to
our
the
range,
ABC
so
that
this
we can
is
type
a
in
function.
x plus 4.
Our domain is the
Notice
x
I
values.
didn't use y
2,
equals.
5,
It kind of
0,
assumes
and
that
4.
for us. But if
And
it
our
makes
range
you
are
feel
all
better,
the
we
y
can say
values.
y is
5,
equal to
7,
these values.
1, and negative
Again,
2.
it gives us
Stop
the
the
x and the
video
y
and see if you
intercepts
can
here,
complete
but I can
C
find more
on your
points
own.
by again clicking on our settings and then clicking on convert to table.
Let's go ahead and make
Notice
the
it doesn't give us
correspondence.
negative 4,
Negative
so
5
you can
goes to
plop that
3.
in.
0
It doesn't
goes
give us
to 3,
negative 3,
and 6
we
goes
can
to
plop
3.
that in.
Since
And
each
we're also
member
looking
in our
for
domain
5.
goes
Notice
to
as I was typing
only
them in
one
again
member
that
of
the
the
points
range,
show
we can
up on
say
our graph
that this
for us,
is
and
a
we can click
function.
these points to
And our
see what they
domain
are.
are the x values, so negative 5, 0, and 6, and our range is just
When
3.
given a graph, and a function
we're going to talk about
itself,
another way
I can
later
use that
on
graph
in
to
this
help
lesson
evaluate
how we can
so I don't
see if
have
it is
to
a function or
substitute,
not by
but you
using the
certainly
vertical
could.
line test.
So if I want to find what
Let's
is
determine
f of
if a
negative
function
3.
f
So notice
given
negative
by
3 is where our
function
x value
notation
is.
f with
So when I look
respect
at
to
my
x
graph and find
is equal
negative
to
3,
2x squared
I see
minus
its y
x plus
correspondence
3.
is
Let's
positive
evaluate
3.
each of the following.
If I want to
So
find
notice
out
my
what is
x
the
value
function
is replaced
at
with
1,
0.
I
So
find
I'm
1,
going to substitute
and
in
I see
my
that its
function
value
everywhere I
corresponds
see
with
x,
negative
I'm
5.
going to replace it with 0.
We can
Giving
also
me
use
2
the
times
vertical
0
line
squared
test. It tells
minus
us that
0
it is,
plus
if
3.
it is possible
Using our
for
order
a
of
vertical line
operations,
to
we
cross a
simplify
graph more
this
than once,
such that
then the
f of
graph
0
is not
corresponds to
a function. So let's
3.
try it out.
Let's do the same for
Here we have
x
a line,
being negative
and
7.
I see if
Everywhere
I
I
draw my
see
vertical
x, I'm
line
going to
anywhere
substitute it with
on
negative 7.
this graph, it only
2
crosses
times
one
negative
time.
7
so
squared
it is
minus
a function.
negative 7 plus 3.
When I look at my
Well,
second
negative
graph,
7
though,
times negative
notice
7
there are
is
a few
49.
places, or
Negative
more than a few,
minus
I should say,
7
that it
is
crosses the
positive
graph
7.
more than
And then
one
using
time.
the order of
So
operations,
the second one
I see that
is
when I
not
plug
a
in
function.
negative 7 to my function, out
And the
pops
third
108.
one here, again, if I
Now, we're not just
drag my
limited
vertical
to
line across,
whole
notice there are
numbers or
extremely more than one
rational
places
numbers
where it
for
would
that
cross
matter
the graph
in our
more than
function.
one
We
time.
can substitute in
So this is
anything
also
we want,
not a
such
function.
as let's substitute 5a.
What if I
in.
look at
so
my circle?
everywhere I see
If I look
x,
at my
I'm going to
circle, I
replace
also
it with
know that it is not
5a.
a function because it
Well,
crosses the
5a
graph
squared
more
is the
than
same
one
as
time.
5a times
When
5a,
I move over
or
to this
25a
weird-looking graph,
squared.
it only
This would then
crosses
give us
each part of the
2
graph
times
one time,
25a
no matter how oddly
squared
shaped it is.
minus
So this
5a
one is
plus
a function.
3.
And the last one is
Simplifying
also
gives
a
us
function.
50a
Notice
squared
that at this
minus
point
5a
right
plus
here,
3. Even though
now there's nothing else
this
we
one
can
has
do
a
since we
closed
still
stop
have a
which means
variable,
included,
so at this point
we can stop.
has an open dot.
We also
so
can
it's
substitute a
excluded.
binomial
So even
into
though
our
they're
equation,
on top of each other and
such as
stacked,
a
one is
minus 4.
excluded
So
and one is
everywhere I
included.
see
So
x, I'm going to
technically,
replace
this
it
is
with
a function.
minus 4. I now need to take a minus 4
Find
squared,
the indicated
which we know
function
is a
values,
minus
if
4
possible,
times
and
a
determine
minus
whether
4.
the given values are in the domain
Using the
of the
distributive
function.
property,
So again, the
we
domain
will distribute
is the
a
x
minus 4
values.
times a
I'm
minus
going to
4
first providing
plug
us
in
with a
f
squared
of 1
minus
for my
4a
function
minus
minus
4a
4a
minus
plus
3.
16.
When I do that
Combining
and
like
simplify my
terms
denominator,
gives us a
I end up
squared
with
minus
negative
half
8a
so
plus
f of
16.
1 is defined.
I now
and
need
it
to
is
distribute
in the domain because
my
we got
2
a nice
in
front
front
of
of
my
number.
trinomial.
However,
and my
when I plug
negative
in
1
3,
in front
I
of
end up
a
with
minus
1
over
4.
3 minus
That would
3.
give us 2a squared.
3
minus
minus
3 is 0.
a plus
So
32
we cannot divide by 0.
minus a.
So 3
plus
is
4
not
plus
defined.
3.
So it's not
Combining
in the domain
like terms,
because we cannot
we
divide
have
by
f
0.
of a minus 4.
So we would
is
want to
equal to 2a
exclude
squared
3
minus
from our
17a
domain and not
plus
have it
39.
listed.
Let's do the same for g of 16 and g of negative 7 for our function square root of x plus 5. Let's start with 16. I know that the square root of 16 is 4 and 4 plus 5 is 9, a nice number. So g of 16 is certainly defined and it is in the domain because we're able to find it. However, when I look at negative 7, I can't take the square root of negative 7 because it would give me an imaginary number or a complex number. When I plug it into my calculator, it doesn't know what to do with it. So square root of negative 7 is not defined as a real number because it's an imaginary complex number. So since it's not defined, negative 7 is not in the domain and we would want to exclude that. Find the domain of each of the following functions. I know that the denominator is crucial and key in determining whether or not something is in the domain and what conditions the function may be under because of it. So we also know that the given will not be in the domain whenever the denominator is equal to 0. So I'm going to start by solving each denominator for 0 because we know whenever it equals 0, it will not be defined. When I set x minus 7 equal to 0 and solve, I get x equal to 7. So x cannot be 7 because if I take 7 and plug it in here, I will end up with 1 over 0 and we know that can't happen. So 7 is not in the domain. There are one of two ways with which we can write this. This first part here says x such that x cannot be 7, Or we can write it from negative infinity to 7, union, meaning we're going to skip 7 and we're going to continue from 7 to infinity. This is what we call set builder notation on the left, and on the right is what we call interval notation. You could write it any way that you see fit. If we were to graph this, there would be a big blank spot at 7 because it's not defined. Let's take a look at what that graph might look like. Notice in our graph, when I have the function f of x is equal to 1 over x minus 7, that our graph is coming from infinity. It's coming. And we hit this wall because our graph is not defined at 7. We're jumping over 7 and then we're continuing through infinity. Notice in part B, our function h of x, we have a polynomial or a trinomial in our denominator. We still have to set it equal to 0. And remember, to solve these, we're going to need to factor. So remember, to factor, we need to find two numbers that multiply to the last term of -3, but yet add to our middle term of 2. So two numbers that multiply to -3 and add to 2 would be 3 times -1 and 3 plus -1. So our two binomial factors are x plus 3 and x minus 1. Now that it's factored, we can set each factored piece equal to 0 and solve, giving us -3 and 1. So -3 and 1 are not in the domain because they would result in a 0 for our denominator. We would write this in set builder notation as x such that x cannot be 3 and x cannot be 1. X cannot be -3 and x cannot be 1. Written in interval notation then, we would start at negative infinity and we would work our way to -3, hop over -3, start from -3 to 1, hop over 1, and continue from 1 to infinity. Please pause the video and graph writing this entire equation into Desmos. Remember to use y for h of x, and you can see that it does jump over -3 and 1. Letter C, f of x is equal to x cubed plus the absolute value of x. We can substitute any value in for x because we can take the absolute value of any number and we can take the cube of any number. So our domain written in set builder notation is x such that x is any real number. Or we can write it in interval notation because if we have any number, it would be from negative infinity to positive infinity. And finally, letter D, we have g of x is equal to the cube root of x minus 1. Our index is odd, and our index is odd tells us that any value of x, we can actually find its root because it's any real number because it's an odd index. Thus, our domain is any real number, so x such that x is a real number, or from negative infinity to positive infinity. And if you were to graph this, you would see that it would move from left to right on our graph without any holes, jumps, or skips. Let's use the graph of the function to find the domain and the range. Again, x is our domain, and our y values are our range. When I take a look at this linear equation, I see that it's going to continually move left to right forever and ever. So my domain goes from negative infinity all the way to positive infinity. The same is true for my range. I'm going to start way down at negative infinity and I'm going to keep going up and up and up and up forever and ever. So my range is also negative infinity to positive infinity. When I look at the domain of my square root function, I see that I can't start at negative infinity over here because there's no graph over here. Our graph starts at -4. So when I put in my domain, I'm going to put a bracket because -4 is included, and my graph is going to continue to positive infinity forever. It's not going to stop. Notice that infinities are used with parentheses, whereas if it's included, it's a bracket. Similarly with our range, I don't have any graph down below. My graph starts at 0. on the y-axis. My graph starts at 0 and it goes to positive infinity, right? Our graph is going to continue extending up forever and ever. So my range is a bracket because we have a y value. This point is negative 4, 0. So my y value is 0. And we're going to continue up forever in the infinity direction. Let's look at this cubic function. Notice that we're going left and right forever and ever. Although it's a slow left and right progress, we still are moving from left to right forever and ever. So negative infinity to positive infinity. The range is easier to see this one because we know it's going to extend downward and upward forever and ever. So negative infinity to positive infinity. When looking at letter D, I see that we have a jump, and notice our jump is at positive 2 here. So when I'm looking at my domain, I'm going to come from negative infinity, and I'm going to come to 2. I'm going to union and skip 2 and continue to positive infinity. Notice that I'm using parentheses here because 2 is not included. Similarly, when I look at my range, notice I have an asymptote at the x-axis. So I have an asymptote when y is equal to 0. So my graph is going to come up from negative infinity. We're going to stop and jump over 0 and continue to positive infinity, which is why we have negative infinity to 0, union or jump over, and go from 0 to infinity. Our next example is a quartic function because it has x to the 4th power. Notice our domain, we're going to extend these arrows to the left and to the right slowly, just like letter C, slowly but surely. So it is going from negative infinity to positive infinity. However, look at our range. There's nothing way down here in our graph. Our graph starts at negative 4 on the y-axis and it moves up. So it moves towards infinity. So our range is from negative 4 inclusive because there are points down here at negative 4 and it goes to infinity. And our last one is a semicircle. Notice our domain. We have 2 places here. We're going to go from 1 to 5 inclusive. So we're going to go from 1 to 5 on the x-axis, and our range, they're also inclusive because these are whole points, go from 0, these points are 1, 0, and 5, 0, go from 0 to 2. The linear expansion L of the steel center span of suspension bridge that is 1,420 meters long is a function of the change in temperature given by this function, where this little tiny number is the coefficient of the linear expansion for steel and L is in meters. Find the linear expansion when our temperature is 30 degrees, 42 degrees, 50 degrees, and 56 degrees Celsius. So notice all we did was replace our temperature with each individual one and evaluate. And I chose to use the table feature in Desmos to help me so that I could easily find these values. And this concludes our lesson on 1.2 when we're looking at graphs of functions.